Imagine trying to measure something so incredibly small that the very act of measurement destroys the meaning of distance itself. Picture a length so minuscule that if you tried to probe smaller distances, space and time would literally break down into quantum foam, where the familiar concepts of here and there cease to exist. This isn't science fiction. This is the Planck length, approximately 10 to 35 meters, and it represents the absolute smallest distance that can possibly exist in our universe. To grasp just how impossibly tiny the Planck length is, consider this. If an atom were scaled up to the size of the observable universe, the Planck length would still be smaller than an atom. It is a distance so small that light, traveling at 300 million meters per second, would take the Planck time of y-43 seconds to cross it. In the time it takes light to travel 1 Planck length, our sun produces less energy than a single quantum of radiation. The Planck length isn't just another very small distance that we might someday measure with better instruments. It represents a fundamental limit imposed by the laws of physics themselves, specifically by the strange marriage between quantum mechanics and gravity that occurs when we try to probe the smallest scales of reality. At distances smaller than the Planck length, our best theories predict that space-time itself becomes so violently unstable that the very notion of distance breaks down completely. Dr. Max Planck first derived this fundamental length in 1899, long before quantum mechanics was fully developed and decades before Einstein's general relativity. Planck was exploring the relationship between fundamental constants of nature, the speed of light, the gravitational constant, and what would become known as Planck's constant. When he combined these constants in the only way that produces a unit of length, he discovered something profound. There exists a natural scale of distance built into the fabric of reality itself. The mathematics is deceptively simple. Take Planck's constant, which governs quantum mechanics. Multiply it by the gravitational constant, which governs space-time curvature. Divide by the speed of light cubed, and take the square root. The result is 1.616 times 10, 35 meters, a distance so small that there are more Planck lengths in a centimeter than there are centimeters in the observable universe. But the Planck length represents far more than just a mathematical curiosity. It emerges from the fundamental tension between two pillars of modern physics: quantum mechanics, which governs the behavior of matter and energy at the smallest scales, and general relativity, which describes how mass and energy curve spacetime at the largest scales. These two theories have never been successfully unified, yet they both contribute to defining this ultimate distance scale. When you try to measure distances smaller than the Planck length, quantum mechanics and gravity conspire to make the measurement impossible. The energy required to probe such small distances is so enormous that it would create microscopic black holes that would immediately evaporate in bursts of Hawking radiation. The very act of measurement would warp spacetime so violently that the concept of distance would lose all meaning. This isn't a limitation of our technology or experimental techniques. It is a fundamental feature of reality itself. Even if we had perfect instruments and unlimited energy, we could never measure distances smaller than the Planck length, because the laws of physics prevent such measurements from having any meaning. We've reached the point where our rulers break reality before reality breaks our rulers. The implications extend far beyond abstract physics. If the Planck length represents the smallest possible distance, then space itself might be fundamentally discrete rather than continuous. Just as matter is made of atoms rather than being infinitely divisible, space might be made of indivisible units of Planck-scale atoms of space. This could mean that the smooth spacetime of Einstein's relativity emerges only at large scales, while the true nature of space is fundamentally quantum and granular. Modern theories of quantum gravity take the Planck length seriously as a fundamental scale where new physics must emerge. String theory proposes that fundamental particles are actually tiny vibrating strings with characteristic sizes near the Planck length. Loop quantum gravity suggests that space itself has a granular structure at the Planck scale, with areas and volumes coming in discrete quantum units. The Planck length also plays a crucial role in cosmology. During the first Planck time after the Big Bang, when the universe was smaller than the Planck length, our current theories of physics break down completely. Understanding what happens at the Planck scale might be the key to understanding how the universe began and whether concepts like before the Big Bang have any meaning. Recent developments in black hole physics suggest that the Planck length might be connected to the fundamental nature of information and entropy in the universe. The holographic principle proposes that all the information in a volume of space is encoded on its boundary, with each Planck length squared area holding exactly one bit of information. If you're fascinated by the fundamental limits of reality and the deepest scales of physics, subscribe and hit thumbs up. And here is something mind-bending to consider. How many Planck lengths do you think exist in the width of a human hair? Comment your calculation below. I'll pin the most creative approach to visualizing this impossible scale. Tonight, we're going to explore how the marriage of quantum mechanics and gravity creates an absolute limit on the measurement of distance, revealing that reality itself has a fundamental granular structure at scales so small they challenge our very concept of what space and time mean. We'll all discover how the Planck length emerges from the deep structure of physical law and why it represents more than just a very small distance. It is the scale where space and time themselves are born. The journey to understanding the Planck length will take us through the quantum foam that underlies all of spacetime, the event horizons of black holes where information itself reaches its limits, and the first moments after the Big Bang when the entire universe was smaller than a subatomic particle, yet contained all the energy and information that would eventually become galaxies, stars, and conscious beings, capable of contemplating the fundamental nature of distance itself. This isn't just about measuring very small things. It is about understanding the basic architecture of reality and discovering that there are absolute limits built into the fabric of existence itself. The Planck length represents humanity's encounter with the deepest possible questions about the nature of space, time, and the fundamental structure of the cosmos. Now let's begin our descent into the quantum depths of spacetime, where distance itself is born, and where the familiar rules of measurement give way to something far stranger and more fundamental. Chapter 1. Scale and Perspective Understanding. Why the Planck length represents the smallest possible distance requires first appreciating the vast hierarchy of scales that exist in our universe, from the cosmic to the quantum, and recognizing how the Planck length fits into this cosmic zoom as the absolute bottom limit of meaningful distance measurement. The scales of nature span more than 60 orders of magnitude, creating a universe where the tiniest and largest structures differ by numbers so vast they strain human comprehension. At the largest scales, the observable universe extends roughly 1,026 meters from edge to edge, containing billions of galaxies, each spanning hundreds of thousands of light years. Galaxy clusters stretch across tens of millions of light years, while the cosmic web of dark matter filaments creates structure on scales approaching the size of the observable universe itself. Descending through the hierarchy of cosmic structure, we encounter individual galaxies like our Milky Way, spanning about YA meters across. Our solar system occupies roughly YD meters from the Sun to the outer reaches of the Kuiper Belt, while Earth itself has a diameter of about 107 meters, a size scale comfortable for human intuition and everyday experience. Human-scale objects typically range from millimeters to kilometers, representing the narrow band of scales where our senses and everyday experience operate effectively. A human being stands roughly 2 meters tall, while the cells that compose our bodies measure about 10 to 5 meters across. These biological structures represent highly organized matter operating at scales where classical physics dominates quantum effects. Atoms, the building blocks of ordinary matter, have typical sizes around 10 to 10 meters. At this scale, quantum mechanical effects begin to dominate classical physics, and the familiar concepts of definite position and momentum start to break down according to Heisenberg's uncertainty principle. Atomic nuclei are roughly 100,000 times smaller than atoms, occupying spaces of about 10 to 15 meters. Protons and neutrons, the particles that make up atomic nuclei, have sizes around 10 to 15 meters and are themselves composed of quarks held together by the strong nuclear force. At these scales, the physics becomes increasingly dominated by quantum field theory and the standard model of particle physics. The smallest distances that have been directly probed by particle accelerators extend down to about y-19 meters, achieved through high-energy collisions at facilities like the Large Hadron Collider. Beyond these experimentally accessible scales lies a vast desert of distance scales that remain largely unexplored by direct measurement. The Planck length exists at 1.616 times 10 to 35 meters, roughly 16 orders of magnitude smaller than anything we can currently probe experimentally. To put this in perspective, the Planck length is smaller relative to a proton than a proton is relative to a human being. If a proton were scaled up to the size of the observable universe, the Planck length would be about the size of a tree. This extreme hierarchy of scales creates fundamental challenges for both theoretical understanding and experimental investigation. Each transition between different scale regimes typically involves new physics principles, emergent phenomena, and different mathematical frameworks for describing physical behavior. Dr. Kenneth Wilson's work on the renormalization group revealed how physics at different scales connects through systematic procedures for relating phenomena at high-energy scales to low-energy effective theories. This work showed that the Planck scale represents a natural cutoff where current effective field theories must be replaced by more fundamental descriptions. The concept of emergence becomes crucial for understanding how familiar physics at large scales arises from more fundamental processes at smaller scales. The smooth spacetime of general relativity might emerge from discrete quantum processes at the Planck scale, just as thermodynamics emerges from statistical mechanics or chemistry emerges from quantum mechanics. Scale invariance and scaling laws reveal deep patterns in how physical systems behave across different size scales. Some phenomena, like critical behavior near phase transitions, exhibit scale-free behavior that looks similar at all length scales. However, the existence of the Planck length suggests that true scale invariance breaks down at the fundamental level. Dimensional analysis provides powerful tools for understanding how physical quantities scale with size and for identifying natural units based on fundamental constants. The Planck units, including the Planck length, time, mass, and energy, represent natural scales built into the structure of physical law rather than arbitrary human conventions. The hierarchy problem in particle physics asks why such enormous differences exist between different physical scales, particularly why gravity is so much weaker than other forces. Understanding this hierarchy might require new physics at intermediate scales between the electroweak scale and the Planck scale. Effective field theory provides the mathematical framework for understanding how physics at different scales relates to each other. At each energy scale, we can write down the most general theory consistent with known symmetries, then determine how that theory connects to physics at other scales through quantum corrections. The mathematical concept of limits becomes physically meaningful when considering the approach to the Planck scale. Just as classical mechanics emerges as a limit of quantum mechanics when quantum effects become negligible, some more fundamental theory might reduce to known physics in the limit where distances are large compared to the Planck length. Holographic principles suggest that the information content of any region of space is determined by the area of its boundary, measured in Planck units rather than by its volume. This implies that the Planck length provides the fundamental unit for measuring information density in spacetime. The anthropic principle takes on new meaning when considering the hierarchy of scales in nature. The enormous range of scales in the universe might be necessary for the emergence of complex structures capable of supporting life and consciousness. Small changes in fundamental constants could alter this hierarchy in ways that prevent complexity from developing. Modern cosmology reveals that the universe has evolved through different scale regimes over cosmic history. During inflation, quantum fluctuations at microscopic scales were stretched to cosmic proportions. The Planck scale represents the ultimate limit where this stretching process must have originated. Quantum field theory in curved spacetime provides the theoretical framework for understanding how quantum effects and gravitational effects interact. At the Planck scale, these effects become comparable in strength, requiring new theoretical approaches that go beyond both quantum field theory and general relativity. The measurement problem in quantum mechanics becomes particularly acute at the Planck scale, where the energy required for precise measurements becomes large enough to significantly disturb spacetime itself. This suggests that the Planck length might represent a fundamental limit on the precision of spatial measurements. String theory proposes that the fundamental constituents of matter are extended objects, strings, rather than point particles. The characteristic size of these strings is expected to be close to the Planck length, suggesting that the Planck scale might be where the true fundamental structure of matter is revealed. Loop quantum gravity approaches the Planck scale from the perspective of spacetime geometry itself, proposing that area and volume are quantized in units involving the Planck length. This approach suggests that spacetime has a discrete structure at the fundamental level. Perhaps most remarkably, the existence of a shortest possible distance suggests that the universe has a fundamental digital rather than analog character. Just as digital computers process information in discrete bits rather than continuous values, space itself might be fundamentally discrete at the Planck scale. The scale hierarchy of nature, culminating in the Planck length as the smallest meaningful distance, reveals that reality is organized as a vast nested structure where different physical principles dominate at different scales. Understanding how this hierarchy emerges and why the Planck scale represents its ultimate foundation remains one of the deepest challenges in theoretical physics. As we'll explore next, the quantum mechanics that governs physics at small scales creates fundamental limitations on measurement precision that become absolute barriers when we reach distances comparable to the Planck length. Chapter 2. Quantum Limits. The quantum mechanical nature of reality imposes fundamental limits on how precisely we can measure distances, and these limits become absolute barriers to meaningful measurement when we approach the Planck length. Understanding these quantum constraints reveals why the Planck length isn't just very small, but represents a fundamental boundary beyond which the concept of distance itself breaks down according to the laws of physics. Heisenberg's uncertainty principle provides the foundation for understanding quantum limits on measurement. The principle states that the more precisely we try to measure the position of a particle, the less precisely we can know its momentum, and vice versa. Mathematically, the uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to Planck's constant divided by 4. This uncertainty relationship has profound implications for distance measurement. To probe very small distances, we need particles or photons with very short wavelengths, which means very high energies and momenta. But high-energy probes create large momentum uncertainties that ultimately limit how precisely we can localize our measurements. Dr. Werner Heisenberg first derived the uncertainty principle in 1927. Showing that it emerges naturally from the wave-like nature of matter and energy at quantum scales. The principle isn't a statement about experimental limitations, but rather a fundamental feature of quantum reality that applies even to perfect measurements with ideal instruments. The relationship between wavelength and resolution in measurement systems means that probing smaller distances requires shorter wavelengths and higher energies. Electron microscopes achieve better resolution than optical microscopes by using electron wavelengths much shorter than visible light wavelengths. To probe the Planck length, we would need wavelengths comparable to the Planck length itself. But creating wavelengths short enough to probe the Planck scale requires energies comparable to the Planck energy, approximately 1019 GeV, or about 2 billion joules. This is roughly the energy contained in 50 liters of gasoline, concentrated into a single quantum particle. Such energies are far beyond anything achievable with current particle accelerators, and approach the energy scales where gravity becomes quantum mechanical. Quantum field theory extends the uncertainty principle to include energy and time uncertainties that become crucial near the Planck scale. The uncertainty principle allows virtual particle-antiparticle pairs to spontaneously appear from the quantum vacuum, borrowing energy for brief periods before annihilating each other. At the Planck scale, these quantum fluctuations become so violent they fundamentally alter the structure of spacetime. The quantum vacuum is an empty space, but rather a seething foam of virtual particles, constantly appearing and disappearing. These vacuum fluctuations create a fundamental graininess to spacetime that becomes pronounced at the Planck scale. The smooth spacetime of classical general relativity emerges only as an average over these quantum fluctuations at larger scales. Dr. John Wheeler coined the term quantum foam to describe the turbulent nature of spacetime at the Planck scale, where quantum fluctuations make the geometry of space and time fluctuate wildly. In this quantum foam, the familiar notions of definite position, distance, and even the topology of space lose their classical meanings. Black hole formation provides another quantum limit on distance measurement at the Planck scale. When we try to concentrate enough energy to probe very small distances, the energy density becomes so high that it forms a black hole. The Schwarzschild radius of this black hole would be comparable to or larger than the distance we were trying to measure, making the measurement impossible. The Bekenstein bound, derived by Dr. Jacob Bekenstein in the 1970s, provides a fundamental limit on how much information can be contained in any region of space. This bound is expressed in terms of the area of the region measured in Planck units, suggesting that the Planck length provides the fundamental scale for information storage in space. Hawking radiation adds another layer of quantum limits to Planck scale physics. Black holes formed during attempts to probe very small distances would immediately evaporate through Hawking radiation, with smaller black holes evaporating faster. Black holes with masses near the Planck mass would evaporate in approximately the Planck time, creating fundamental limits on the duration of any measurement process. The holographic principle, emerging from black hole physics, suggests that all the information in any volume of space is encoded on its boundary, with each Planck area element of the boundary containing exactly one bit of information. This principle implies that the three-dimensional volume we experience emerges from more fundamental two-dimensional physics at the Planck scale. Quantum error correction becomes impossible at the Planck scale due to the fundamental limitations on information storage and processing imposed by quantum mechanics and gravity. The no-cloning theorem prevents perfect copying of quantum information, while gravitational effects create fundamental noise that cannot be corrected below the Planck scale. The measurement problem in quantum mechanics becomes particularly acute when considering Planck scale distances. Classical measurement devices cannot exist at these scales, and any quantum measurement system would itself be subject to the same quantum uncertainties we're trying to measure. This creates a fundamental bootstrap problem for Planck scale metrology. Entanglement and non-locality at the Planck scale could fundamentally alter our understanding of distance and spatial relationships. Quantum entanglement allows instantaneous correlations between spatially separated systems, potentially making the classical concept of distance irrelevant for quantum information processing at the Planck scale. The relativistic quantum limit emerges when quantum effects and relativistic effects become comparable, which occurs naturally at the Planck scale. The Klein-Gordon and Dirac equations describe relativistic quantum mechanics, but these equations break down when applied to distances comparable to the Planck length. Casimir effect demonstrates how quantum vacuum fluctuations create measurable forces between macroscopic objects separated by small distances. At the Planck scale, these vacuum fluctuations become so strong they would overwhelm any attempt to maintain stable reference points for distance measurement. Quantum tunneling allows particles to pass through energy barriers that would be insurmountable in classical physics. At the Planck scale, quantum tunneling becomes so probable that particles could tunnel arbitrary distances through spacetime, making the concept of definite position meaningless. The uncertainty principle for time and energy creates temporal limits that complement spatial limits at the Planck scale. The Planck time represents the shortest meaningful time interval during which light travels exactly one Planck length. Attempts to measure shorter times or distances run into fundamental quantum mechanical limitations. Quantum decoherence describes how quantum systems lose their quantum coherence through interaction with their environment. At the Planck scale, decoherence occurs so rapidly that maintaining the quantum coherence necessary for precise measurements becomes impossible over any meaningful time scale. The many-worlds interpretation of quantum mechanics suggests that measurement at the Planck scale might involve fundamental splits in reality itself. Each quantum measurement might create multiple universe branches, making the concept of a single definite measurement result meaningless. Quantum field theory in curved spacetime shows how quantum effects and gravitational effects interact near the Planck scale. The stress-energy tensor includes contributions from quantum vacuum fluctuations that become significant at the Planck scale, potentially creating feedback loops between quantum effects and spacetime curvature. Perhaps most fundamentally, the quantum limits on distance measurement suggest that space itself might be fundamentally discrete rather than continuous. Just as energy and angular momentum are quantized in quantum mechanics, space and time might come in indivisible units of Planck length and Planck time. The implications extend beyond pure physics to questions about the nature of reality itself. If quantum mechanics prevents meaningful measurements below the Planck scale, this might indicate that smaller distances simply don't exist rather than being merely unmeasurable. The Planck length might represent the pixel size of reality itself. As we'll explore next, the gravitational effects that become dominant at the Planck scale create additional fundamental barriers to measurement that reinforce and extend the quantum limits on distance resolution. Chapter 3. Gravitational effects. When we attempt to measure distances near the Planck length, gravitational effects become so dominant that they fundamentally alter the nature of spacetime itself, creating absolute barriers to measurement that complement and extend the quantum mechanical limits we've already explored. At the Planck scale, gravity transitions from being the weakest force in nature to becoming comparable in strength to the other fundamental forces. Einstein's general theory of relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. This curvature becomes extremely pronounced when high concentrations of energy are present in small regions of space, exactly the conditions required to probe very small distances through high-energy particle interactions. The Schwarzschild radius provides a fundamental gravitational limit on how much mass or energy can be concentrated in a given region before it collapses into a black hole. For any spherically symmetric mass m, the Schwarzschild radius is Rs equals 2 gm per c squared, where g is the gravitational constant and c is the speed of light. When matter is compressed within this radius, it forms an event horizon from which nothing can escape. To probe distances of order the Planck length, we need energy concentrations approaching the Planck energy of about 1019 GeV. When this much energy is concentrated in a region the size of the Planck length, the resulting energy density exceeds the threshold for black hole formation. The Schwarzschild radius of such a concentration would be comparable to or larger than the Planck length itself. Dr. John Wheeler first recognized this fundamental connection between quantum mechanics and gravity in the 1950s, showing that attempts to measure very small distances inevitably create gravitational fields strong enough to form black holes. This represents a fundamental barrier to measurement that cannot be overcome by any conceivable improvement in experimental technique. The formation of microscopic black holes during high-energy measurements creates a fundamental uncertainty in the measurement process. The black hole would immediately begin evaporating through Hawking radiation, but during its brief existence, it would completely scramble any information about the precise spatial relationships we were trying to measure. Hawking radiation, discovered by Dr. Stephen Hawking in 1974, shows that black holes are not perfectly black but emit thermal radiation with a temperature inversely proportional to their mass. Smaller black holes are hotter and evaporate faster than larger ones. A black hole with a mass equal to the Planck mass would evaporate completely in approximately the Planck time. The evaporation of microscopic black holes through Hawking radiation creates fundamental limits on information storage and retrieval at the Planck scale. Any information that falls into such a black hole would be scrambled and then radiated away as thermal Hawking radiation, making precise spatial measurements impossible. Tidal forces near black holes become extreme at the Planck scale, where the gravitational field gradients are enormous. These tidal forces would tear apart any conceivable measuring device long before it could provide useful information about distances comparable to the Planck length. The very atoms of any measurement apparatus would be disrupted by gravitational effects. The event horizon of a Planck mass black hole has an area of approximately 1 Planck area, the square of the Planck length. According to the holographic principle, this horizon can store at most 1 bit of information, representing the fundamental limit on information density in space. Spacetime curvature at the Planck scale becomes so extreme that the flat spacetime assumptions underlying special relativity completely break down. The metric tensor describing spacetime geometry fluctuates wildly due to quantum effects, making it impossible to define consistent coordinate systems for distance measurement. The equivalence principle, which states that gravitational and acceleration effects are locally indistinguishable, becomes problematic at the Planck scale. The principle relies on the existence of local inertial frames, but quantum gravitational effects make it impossible to define such frames consistently over distances comparable to the Planck length. Geodesic deviation, which describes how nearby geodesics, straight lines in curved spacetime, diverge due to tidal forces, becomes extreme at the Planck scale. This deviation would make it impossible to maintain the parallel reference trajectories necessary for precise distance measurements in strongly curved spacetime. The stress-energy tensor in Einstein S-field equations receives contributions from quantum vacuum fluctuations that become significant at the Planck scale. These quantum contributions to the stress-energy tensor create feedback loops between spacetime, curvature, and quantum effects that make the field equations fundamentally nonlinear and chaotic. Gravitational waves, ripples, and spacetime itself are constantly being produced by accelerating masses throughout the universe. At the Planck scale, these gravitational wave fluctuations become so intense that they create a fundamental background noise that would overwhelm any attempt at precise spatial measurements. The Planck mass, approximately 2.2 times 10⁻⁸ kilograms, represents the mass scale where gravitational and quantum effects become comparable. This might seem like a tiny mass by everyday standards, but when concentrated in a region the size of the Planck length, It creates gravitational effects comparable to those of macroscopic black holes. Wormhole formation becomes possible at the Planck scale, where quantum fluctuations could create temporary connections between distant regions of spacetime. These quantum wormholes would make the very concept of spatial distance ambiguous by providing alternate pathways between points in space. The Wheeler-DeWitt equation attempts to describe the quantum mechanics of spacetime itself, but it becomes particularly important at the Planck scale, where quantum effects and gravitational effects are equally important. Solutions to this equation suggest that spacetime might have a fundamentally discrete structure at the Planck scale. Causal structure becomes problematic at the Planck scale because extreme spacetime curvature can create closed time-like curves and other violations of causality. The normal causal relationships between events, which are essential for meaningful distance measurements, break down when gravitational effects become this extreme. The cosmological constant problem illustrates how quantum effects and gravitational effects interact at the Planck scale. Quantum field theory predicts that vacuum fluctuations should contribute an enormous energy density to spacetime curvature, but observations show that the actual cosmological constant is many orders of magnitude smaller than these predictions. Singularity theorems, developed by Roger Penrose and Stephen Hawking, show that general relativity inevitably predicts the formation of singularities, where spacetime curvature becomes infinite. At the Planck scale, quantum effects might prevent these singularities from forming, but only by fundamentally altering the structure of spacetime. The information paradox for black holes becomes particularly relevant at the Planck scale, where microscopic black holes constantly form and evaporate. If information is preserved during black hole evaporation, as quantum mechanics requires, then the Hawking radiation must encode information about the spatial structure that fell into the black hole. Quantum foam represents the combination of quantum and gravitational effects at the Planck scale, where spacetime itself undergoes constant quantum fluctuations. In this foam, the metric tensor describing spacetime geometry fluctuates so rapidly that the very concept of a smooth spacetime manifold breaks down. The holographic principle suggests that gravitational effects at the Planck scale might be described by theories living on low-dimensional boundaries of spacetime regions. This could mean that the three-dimensional space we experience emerges from more fundamental physics operating in fewer dimensions. Perhaps most remarkably, the dominance of gravitational effects at the Planck scale suggests that understanding distance at the shortest scales requires a complete theory of quantum gravity that unifies general relativity with quantum mechanics. Until such a theory is developed, the Planck length remains the fundamental barrier beyond which our current understanding of space and time breaks down. The gravitational effects at the Planck scale don't just complement quantum limits on measurement. They create an entirely new category of physical phenomena where spacetime itself becomes a quantum mechanical system, subject to uncertainty principles, fluctuations, and non-local correlations that make classical concepts of distance meaningless. As we'll explore next, these quantum gravitational effects reveal that space and time themselves might have a fundamentally discrete structure, making the Planck length not just a measurement limit, but the actual pixel size of reality. Chapter 4. Spacetime foam at the Planck scale. The smooth, continuous spacetime of our everyday experience dissolves into a chaotic quantum foam where the very concepts of space and time undergo violent fluctuations that make traditional notions of distance completely meaningless. This quantum foam represents the deepest level of physical reality, where spacetime itself becomes subject to uncertainty principles and quantum mechanical effects. Dr. John Wheeler first introduced the concept of spacetime foam in the 1950s, recognizing that when quantum mechanics and general relativity are combined, they predict that spacetime geometry must undergo quantum fluctuations at the Planck scale. These fluctuations are so violent that the smooth spacetime manifold assumed by classical general relativity completely breaks down. The physical picture of spacetime foam emerges from applying the uncertainty principle to the geometry of space itself. Just as quantum mechanics requires uncertainty in the position and momentum of particles, quantum gravity requires uncertainty in the metric tensor that describes spacetime geometry. At the Planck scale, these metric fluctuations become so large that spacetime loses its classical character. In the quantum foam, virtual black holes constantly appear and disappear through quantum tunneling processes. These microscopic black holes have masses near the Planck mass and lifetimes near the Planck time, existing for just y-43 seconds before evaporating through Hawking radiation. During their brief existence, they create regions where spacetime curvature becomes extreme. The topology of spacetime itself becomes unstable in the quantum foam. While classical spacetime has a fixed topology, the property that determines how space is connected, quantum effects allow the topology to fluctuate. Wormholes can spontaneously appear and disappear, temporarily connecting distant regions of space before pinching off and vanishing. Dr. Stephen Hawking's work on Euclidean quantum gravity provided mathematical tools for studying spacetime foam through path integral methods. In this approach, all possible spacetime geometries contribute to quantum mechanical amplitudes, with the most probable geometries being those that minimize the Euclidean action. This leads to predictions about the statistical properties of spacetime fluctuations. The fractal nature of spacetime foam means that it exhibits structure at all scales smaller than the Planck length. But this structure is so complex and chaotic that it defies description using traditional geometric concepts. The surface of spacetime, when viewed at sufficient magnification, reveals an infinite hierarchy of structure that never settles down to a smooth manifold. Causal structure breaks down in spacetime foam because quantum fluctuations in geometry can create closed time-like curves, regions where cause and effect relationships become circular. Light cones, which normally define the causal relationships between events, fluctuate wildly and can even flip orientation in extreme quantum fluctuations. The concept of distance becomes problematic in spacetime foam because geodesics, the paths that define shortest distances between points, constantly fluctuate due to the changing geometry. What appears to be the shortest path between 2 points at one moment becomes a longer path the next moment as the foam undergoes quantum evolution. Coordinate systems lose their meaning in spacetime foam because the extreme fluctuations make it impossible to maintain consistent reference frames. Any attempt to establish a coordinate grid gets disrupted by the violent quantum fluctuations in geometry, making it impossible to assign definite coordinates to events. The measurement of areas and volumes becomes fundamentally uncertain in spacetime foam due to the quantum fluctuations in geometry. Even the concept of a well-defined three-dimensional volume becomes meaningless when the spatial geometry is constantly changing due to quantum effects. Loop quantum gravity provides one approach to understanding spacetime foam through its proposal that space has a discrete structure at the Planck scale. In this theory, areas and volumes are quantized, with the smallest possible area being proportional to the Planck area and the smallest volume being proportional to the Planck volume. Dr. Carlo Rovelli and others have developed loop quantum gravity into a framework where spacetime emerges from more fundamental quantum mechanical degrees of freedom associated with discrete geometric structures. These quantum states of geometry replace the classical spacetime continuum with a discrete network of quantum mechanical relationships. String theory approaches spacetime foam through the dynamics of fundamental strings moving in higher dimensional spaces. The strings themselves have sizes comparable to the Planck length, and their vibrations create the appearance of particles and forces in the lower dimensional spacetime that we experience. The holographic principle suggests that spacetime foam might be described by theories living on the boundaries of spacetime regions rather than in their interiors. This could mean that the three-dimensional foam we've been discussing emerges from more fundamental, two-dimensional physics operating on holographic screens. Information processing becomes fundamentally limited in spacetime foam due to the constant quantum fluctuations that scramble any attempt to store or transmit information reliably. The foam acts like an extremely noisy communication channel that destroys information faster than it can be processed or transmitted. Entanglement plays a crucial role in spacetime foam, with quantum correlations potentially extending across macroscopic distances through the complex topology of the foam. Some theories suggest that spacetime itself emerges from the entanglement structure of more fundamental, quantum mechanical degrees of freedom. The cosmological implications of spacetime foam are profound, as the early universe during the Planck epoch would have been completely dominated by foam-like quantum fluctuations. Understanding how smooth spacetime emerged from this primordial foam might be key to understanding cosmic evolution and the origin of the universe. Black hole interiors provide natural laboratories for studying spacetime foam because the extreme curvature near singularities might reveal foam-like structure that is normally hidden at larger scales. The information paradox for black holes might be resolved by understanding how information is processed in spacetime foam. Thermodynamic properties of spacetime foam suggest that it might have a temperature and entropy associated with the quantum fluctuations in geometry. These thermodynamic properties could provide clues about how to formulate a complete theory of quantum gravity. The emergence of classical spacetime from quantum foam represents one of the deepest unsolved problems in theoretical physics. Understanding how the smooth spacetime of general relativity emerges as a large-scale average over quantum fluctuations in the foam requires new mathematical tools and physical insights. Experimental signatures of spacetime foam remain elusive because the effects are suppressed by enormous factors when averaged over scales much larger than the Planck length. However, some theories predict that precision measurements of gravitational waves or other phenomena might eventually reveal indirect evidence for foam-like structure. The philosophical implications of spacetime foam challenge our basic concepts of reality, suggesting that space and time, the stage upon which all physical phenomena unfold, are themselves emergent phenomena arising from more fundamental, quantum mechanical processes that operate below the threshold of classical physics. Perhaps most remarkably, spacetime foam suggests that the Planck length represents not just a limitation on measurement, but an indication that space itself is fundamentally discrete and quantum mechanical. The smooth, continuous space of our experience would then be like the smooth flow of water, which appears continuous but actually consists of discrete water molecules. The study of spacetime foam reveals that the Planck length marks the scale where the classical concepts of space, time, and distance give way to something far more exotic and quantum mechanical. Understanding this transition from classical to quantum geometry represents one of the greatest challenges in modern theoretical physics. As we'll explore next, the fundamental constants of nature combine in a very special way to define the Planck length, suggesting that this distance scale is built into the basic structure of physical law rather than being an arbitrary human convention. Chapter 5. Fundamental Constants. The Planck length emerges not from arbitrary human conventions, but from the deep structure of physical law itself, arising from a unique combination of the most fundamental constants in nature: the speed of light, the gravitational constant, and Planck's constant. These constants represent the basic parameters that define how our universe operates, and their combination reveals natural units that appear to be built into the fabric of reality. The speed of light in vacuum, denoted c, and equal to approximately 299,792,458 meters per second, represents the maximum speed at which information or energy can propagate through space. Einstein's special relativity revealed that this isn't just the speed of light, but the fundamental speed limit of spacetime itself, connecting space and time into a unified four-dimensional structure. The gravitational constant g, approximately 6.674 times 10⁻11 cubic meters per kilogram per second squared, determines the strength of gravitational interactions between masses. Newton first introduced this constant to quantify the universal law of gravitation, but Einstein's general relativity revealed that g actually determines how mass and energy curve spacetime geometry. Planck's constant h, approximately 6.626 times 10 to 34 joule seconds, quantifies the fundamental quantum of action in nature. Max Planck introduced this constant in 1900 to explain black-body radiation, discovering that energy comes in discrete packets proportional to frequency. The reduced Planck constant A equals h2 pi often appears in quantum mechanical equations. Dr. Max Planck first derived natural units from these fundamental constants in 1899, well before the full development of quantum mechanics or general relativity. Planck was exploring dimensional analysis, the study of how physical quantities scale with basic units, when he discovered that certain combinations of C, G, and A produce fundamental units of length, time, mass, and energy. The Planck length is defined as Lp equals square root Ag per c cubed, combining all three fundamental constants in the unique way that produces a unit of length. This combination is not arbitrary. It is the only way to construct a length scale from these three constants using dimensional analysis. Any other combination would produce units of time, mass, energy, or some other physical quantity. Similarly, the Planck time Tp equals square root ggc represents the time it takes light to travel one Planck length. The numerical values of the Planck units reveal their extraordinary scale. The Planck length is approximately 1.616 times 10 to 35 meters. The Planck time is about 5.391 times 10 to 44 seconds. The Planck mass is roughly 2.176 times 10⁻8 kilograms, and the Planck energy is approximately 1.956109 joules. These scales are far removed from everyday human experience. The Planck length is smaller than an atom by the same factor that an atom is smaller than a continent. The Planck time is shorter than a second by more orders of magnitude than a second is shorter than the age of the universe. Yet these scales might represent the most fundamental units of space and time. The appearance of all three fundamental constants in the definition of Planck length suggests that this scale represents the unique point where quantum mechanics, gravity, and special relativity all become equally important. At larger scales, one or more of these effects can be neglected, but at the Planck scale, all three must be considered simultaneously. Dr. John Wheeler emphasized that the Planck units represent God-s units, natural units built into the structure of reality rather than arbitrary human conventions like meters or seconds. These units would be meaningful to any intelligent civilization anywhere in the universe, representing universal constants of nature rather than parochial human measurements. The fine structure constant alpha, approximately equals 137th, provides another fundamental dimensionless constant that doesn't depend on units. This constant characterizes the strength of electromagnetic interactions and appears throughout atomic physics. While it doesn't directly enter the definition of Planck length, it represents another fundamental parameter of nature. The hierarchy of fundamental constants reveals deep structure in physical law. The gravitational constant is much smaller than other force constants when expressed in natural units, creating the hierarchy problem. Why is gravity so much weaker than other fundamental forces? Understanding this hierarchy might require new physics beyond the standard model. Varying constants theories, proposed that fundamental constants might actually change over cosmic time or space. If confirmed, such variations would profoundly affect our understanding of natural units and might indicate that the Planck length itself evolves over cosmic history. The anthropic principle suggests that fundamental constants must lie within narrow ranges that allow complex structures and life to develop. Small changes in Cg or A would alter the Planck length and might prevent the formation of atoms, stars, or biological systems capable of measuring these constants. Dimensional analysis using fundamental constants provides powerful tools for estimating physical quantities in regimes where detailed calculations are impossible. By constructing quantities with the appropriate dimensions from fundamental constants, physicists can often predict the order of magnitude of unknown effects. The renormalization group in quantum field theory reveals how the effective values of constants change with energy scale. However, the combination of constants that defines the Planck length appears to be renormalization group invariant, suggesting that this natural unit remains meaningful across all energy scales. String theory predicts relationships between fundamental constants that could potentially explain their observed values. In some string models, the Planck length emerges as the characteristic size of fundamental strings, while the other constants are determined by the geometry of extra dimensions. Loop quantum gravity approaches fundamental constants from the perspective of discrete spacetime geometry. In this framework, the Planck area represents the minimum possible area, while the Planck length emerges from the discrete structure of space itself. The holographic principle relates the fundamental constants to information storage capacity in spacetime. Each Planck area can store at most 1 bit of information, suggesting that the Planck length provides the fundamental scale for information density in the universe. Quantum field theory in curved spacetime reveals how fundamental constants enter the equations governing quantum effects near black holes and during cosmological evolution. The interplay between these constants determines phenomena like Hawking radiation and vacuum decay rates. The measurement of fundamental constants has achieved extraordinary precision through atomic physics, gravitational wave astronomy, and other experimental techniques. However, the values of these constants cannot be predicted from current theories. They must be measured experimentally. Unified theories attempt to derive the values of fundamental constants from more basic principles. Grand unified theories try to explain the relative strengths of different forces, while theories of quantum gravity seek to derive the gravitational constant from quantum mechanical principles. The stability of fundamental constants over cosmic time has been tested through astronomical observations of distant quasars, measurements of primordial nucleosynthesis, and studies of natural nuclear reactors. These tests constrain possible variations to extremely small levels. Perhaps most remarkably, the existence of natural units defined by fundamental constants suggests that the universe has an intrinsic set of scales built into its basic structure. The Planck length represents not just a convenient unit for physicists, but possibly the fundamental pixel size of reality itself. The combination of quantum mechanics, relativity, c, and gravity, g, in the definition of Planck length suggests that understanding the smallest possible distance requires a theory that unifies all 3 of these pillars of modern physics. Such a theory of quantum gravity remains one of the greatest challenges in theoretical physics. As we'll explore next, the attempts to create such a unified theory of quantum gravity reveal why the Planck length might represent not just a theoretical concept, but the actual scale where space and time emerge from more fundamental quantum mechanical processes. Chapter 6: Quantum Gravity. The quest to understand why the Planck length represents the smallest possible distance leads directly to one of physics' greatest challenges: developing a theory of quantum gravity that unifies general relativity with quantum mechanics. At the Planck scale, these two pillars of modern physics become equally important, creating a regime where neither theory alone can describe reality adequately. General relativity describes gravity as the curvature of spacetime caused by mass and energy, treating spacetime as a smooth four-dimensional manifold. Quantum mechanics describes matter and energy in terms of probability waves and discrete quantum states. These frameworks use fundamentally different mathematical languages and make different assumptions about the nature of space, time, and matter. The incompatibility becomes apparent when we try to apply quantum mechanics to gravitational fields, or when gravitational effects become important in quantum systems. Quantum field theory assumes a fixed spacetime background on which quantum fields fluctuate, but general relativity tells us that spacetime itself is dynamical and subject to Einstein's field equations. Dr. Bryce DeWitt first attempted to quantize general relativity in the 1960s by treating the metric tensor as a quantum mechanical operator subject to uncertainty principles. This approach leads to the Wheeler-DeWitt equation, a quantum mechanical equation for the wave function of the universe itself. But the resulting theory faces severe technical and conceptual challenges. The problem of time emerges when trying to quantize general relativity because the theory has no preferred time coordinate. All coordinate systems are equivalent. Quantum mechanics, however, requires a time parameter to describe how quantum states evolve. Resolving this conflict requires fundamentally new approaches to understanding time at the quantum level. Renormalization problems plague attempts to apply standard quantum field theory techniques to gravity. While quantum field theories of the electromagnetic and weak nuclear forces can be made mathematically consistent through renormalization procedures, quantum general relativity generates infinite quantities that cannot be removed through any known mathematical technique. String theory represents the most developed approach to quantum gravity, proposing that fundamental particles are not point objects but tiny, one-dimensional strings vibrating in higher dimensional space. The characteristic size of these strings is expected to be close to the Planck length, making string theory naturally applicable at the scale where quantum gravitational effects become important. In string theory, the smooth spacetime of general relativity emerges as a low-energy approximation to more fundamental string dynamics. The violent quantum fluctuations that create spacetime foam at the Planck scale are described as quantum fluctuations in string positions and orientations, providing a concrete physical picture of quantum gravitational phenomena. Dr. Edward Witten and others have shown that string theory naturally incorporates both quantum mechanics and general relativity, with Einstein's equations emerging as equations of motion for the string background. This suggests that string theory might provide the unified description of quantum gravity that has eluded physicists for decades. Loop quantum gravity takes a fundamentally different approach by attempting to quantize spacetime geometry directly, without assuming any background structure. This theory proposes that space has a discrete structure at the Planck scale, with areas and volumes coming in indivisible quantum units proportional to powers of the Planck length. Dr. Carlo Rovelli, Lee Smolin, and others developed loop quantum gravity through a mathematical technique called the Ashtekar formulation, which reformulates general relativity in terms of gauge fields similar to those used in quantum field theory. This allows the application of standard quantization procedures directly to spacetime geometry. In loop quantum gravity, the Planck length emerges naturally as the fundamental scale of spatial discreteness. The theory predicts that areas cannot be smaller than the Planck area and that volumes cannot be smaller than the Planck volume, providing a natural ultraviolet cutoff that eliminates the infinities that plague other approaches to quantum gravity. Causal dynamical triangulation represents another approach to quantum gravity that builds spacetime from fundamental discrete building blocks. In this framework, spacetime is constructed from simple geometric pieces called simplices, with the Planck length setting the characteristic size of these fundamental units. Emergent gravity theories propose that gravitational interactions themselves emerge from more fundamental, quantum mechanical processes, similar to how thermodynamics emerges from statistical mechanics. These approaches suggest that spacetime and the Planck length are not fundamental, but arise from underlying quantum information processing. Dr. Eric Verlind has developed entropic gravity theories, where gravitational forces arise from statistical mechanical effects associated with information storage on holographic screens. In these theories, the Planck length emerges as the fundamental scale for information density, rather than being a primary feature of spacetime geometry. The ADS-CFT correspondence, discovered by Dr. Juan Maldacena, provides a concrete example of how quantum gravity in higher dimensional spaces can be equivalent to quantum field theories without gravity in lower dimensional spaces. This holographic duality suggests that quantum gravity might be fundamentally lower dimensional than it appears. Asymptotic safety represents an approach to quantum gravity that attempts to make Einstein's theory of general relativity mathematically consistent at all energy scales through the existence of a non-trivial fixed point of the renormalization group. If successful, this would make the Planck length a natural cutoff scale for gravitational physics. Black hole thermodynamics provides crucial constraints on any theory of quantum gravity through relationships between black hole area, entropy, and temperature. The fact that black hole entropy scales with area rather than volume suggests that quantum gravity might be fundamentally holographic, with the Planck length setting the fundamental scale. The information paradox for black holes represents one of the most important unsolved problems in quantum gravity. Understanding how information is preserved during black hole evaporation might require new insights into the nature of spacetime at the Planck scale and could reveal fundamental principles governing quantum gravitational physics. Cosmological applications of quantum gravity are crucial for understanding the very early universe, when quantum gravitational effects dominated cosmic evolution. The Planck epoch, lasting from time zero until the Planck time after the Big Bang, represents a period when the universe was so small and dense that quantum gravity effects controlled its dynamics. Inflationary cosmology might require quantum gravitational physics to explain how the universe began and why it underwent rapid expansion during its earliest moments. The fluctuations that eventually became galaxies and large-scale structure might have originated as quantum gravitational fluctuations during the Planck epoch. Laboratory tests of quantum gravity remain extremely challenging because the effects are typically suppressed by enormous factors involving the ratio of laboratory energy scales to the Planck energy. However, precision measurements of gravitational interactions or tests of the equivalence principle might eventually reveal quantum gravitational corrections. Gravitational wave astronomy provides new opportunities to test quantum gravity through precision measurements of spacetime dynamics. Future gravitational wave detectors might be sensitive enough to detect quantum gravitational effects or signatures of the discrete structure of spacetime predicted by some quantum gravity theories. The measurement problem in quantum mechanics becomes even more complex in quantum gravity because spacetime itself becomes quantum mechanical. Understanding how classical spacetime emerges from quantum gravitational states represents a fundamental challenge that goes beyond traditional questions about quantum measurement. Perhaps most importantly, quantum gravity theories suggest that the Planck length represents the scale where the classical concept of distance breaks down completely. Rather than being a limit on measurement, the Planck length might indicate that space itself is fundamentally discrete, emergent, or holographic in nature. The development of a complete theory of quantum gravity would likely revolutionize our understanding of space, time, and the fundamental nature of reality. Such a theory would explain not only why the Planck length represents the smallest possible distance, but also how space and time themselves emerge from more basic quantum mechanical processes. As we'll explore next, The discrete structure of space that emerges from quantum gravity theories suggests that the Planck length might literally represent the pixel size of reality, the smallest unit from which all larger distances are constructed. Chapter 7. Digital Spacetime. The possibility that space and time have a fundamentally discrete structure at the Planck scale suggests that reality itself might be digital rather than analog, with the Planck length serving as the basic pixel size from which all larger distances are constructed. This digital view of spacetime represents a radical departure from the continuous geometries assumed by classical physics, and could revolutionize our understanding of space, time, and information. The concept of discrete spacetime emerges naturally from several approaches to quantum gravity, all suggesting that the smooth, continuous spacetime of classical physics is only an approximation that breaks down at the Planck scale. Just as matter appears continuous in our everyday experience, but actually consists of discrete atoms, space and time might appear continuous, but actually be made of indivisible units. Loop quantum gravity provides the most developed framework for understanding discrete spacetime structure. In this theory, areas and volumes are quantized, meaning they come in discrete multiples of fundamental units. The smallest possible area is proportional to the Planck area, while the smallest possible volume is proportional to the Planck volume. Dr. Carlo Rovelli has shown that in loop quantum gravity, the geometry of space is described by quantum states associated with discrete networks of relationships rather than continuous coordinate systems. These networks, called spin networks, encode the geometric properties of space in a fundamentally discrete way, with the Planck length setting the characteristic scale. The quantization of area in loop quantum gravity means that any surface can be divided into discrete patches, each with area equal to an integer multiple of the Planck area. This discretization applies to all surfaces, including the event horizons of black holes, providing a natural explanation for the discrete nature of black hole entropy. Causal set theory, developed by Raphael Sorkin and others, proposes that spacetime is fundamentally composed of discrete events with causal relationships between them. In this framework, spacetime emerges from the statistical properties of large numbers of discrete causal relationships, with the Planck scale setting the characteristic spacing between events. The holographic principle suggests another form of digital spacetime where all information in any volume of space is encoded on its boundary. If each Planck area of boundary surface encodes exactly one bit of information, then space becomes fundamentally digital from an information-theoretic perspective, regardless of its geometric structure. Dr. Gerard de Hooft has proposed that spacetime might be fundamentally discrete, based on the finite information capacity implied by black hole thermodynamics. If black holes can store only a finite amount of information proportional to their surface area, this suggests that space itself has a discrete information structure at the Planck scale. Spin foam models extend the discrete structure of loop quantum gravity to include time by describing spacetime as a collection of discrete geometric building blocks. These four-dimensional building blocks evolve through quantum mechanical processes that preserve the discrete nature of geometry while allowing for dynamical evolution. The relationship between discrete spacetime and computation becomes particularly important when considering whether the universe might be fundamentally computational in nature. If space and time are digital, then physical processes might be equivalent to computational processes operating on a discrete spacetime substrate. Digital physics theories propose that the universe is literally a computational process, with the Planck length representing the spatial resolution of the cosmic computer and the Planck time representing its temporal resolution. In these theories, physical laws emerge as computational algorithms operating on discrete spacetime data structures. Cellular automata provide mathematical models for how complex phenomena can emerge from simple rules operating on discrete spatial and temporal grids. Some researchers have explored whether spacetime itself might be a cellular automaton with the Planck length and Planck time setting the grid spacing. The emergence of continuous spacetime from discrete fundamentals represents one of the most challenging aspects of digital spacetime theories. Understanding how the smooth spacetime of general relativity emerges from discrete quantum processes requires new mathematical tools and physical insights about how continuous phenomena arise from discrete substrates. Statistical mechanics provides one approach to understanding this emergence, suggesting that continuous spacetime might arise as a thermodynamic limit of discrete quantum gravitational systems. Just as continuous fluid mechanics emerges from the statistical behavior of discrete molecules, continuous spacetime might emerge from discrete geometric degrees of freedom. Renormalization group techniques might explain how discrete spacetime structure at the Planck scale gives rise to continuous effective descriptions at larger scales. As we average over microscopic discrete fluctuations, the effective description becomes increasingly smooth and continuous. The cosmological implications of discrete spacetime are profound, as the Big Bang singularity would be replaced by discrete quantum processes operating at the Planck scale. The apparent singularities predicted by classical general relativity might be artifacts of assuming continuous spacetime where discrete quantum effects actually dominate. Dr. Martin Bajould and others have used loop quantum cosmology to study how discrete quantum geometry affects the very early universe. Their work suggests that the Big Bang might be replaced by a quantum bounce, where the universe contracts to the Planck scale before expanding again, avoiding the classical singularity. Observational signatures of discrete spacetime might be detectable through precision measurements of gravitational waves, cosmic microwave background radiation, or high-energy astrophysical phenomena. However, these effects would typically be suppressed by enormous factors involving ratios of observable scales to the Planck scale. The relationship between discrete spacetime and quantum mechanics raises fundamental questions about the nature of quantum states and measurement processes. If spacetime itself is quantum mechanical and discrete, then the quantum mechanical description of matter and energy must be formulated in terms of discrete, rather than continuous variables. Information theory becomes crucial for understanding discrete spacetime because discrete systems naturally store and process information in digital form. The fundamental limit of 1 bit per Planck area suggested by the holographic principle might reflect the digital nature of spacetime information processing. Quantum error correction might play a crucial role in maintaining the coherence of quantum information stored in discrete spacetime. Just as quantum computers require error correction to maintain quantum coherence, discrete spacetime might require natural error correction mechanisms to maintain geometric coherence. The computational complexity of simulating discrete spacetime systems provides constraints on possible theories of quantum gravity. If spacetime is fundamentally computational, then the universe must be computationally efficient enough to evolve itself, potentially constraining the complexity of quantum gravitational dynamics. Quantum field theory on discrete spacetime requires new mathematical formulations that respect the discrete structure while reproducing continuous field theory in appropriate limits. This leads to lattice field theory approaches where quantum fields are defined on discrete spacetime grids. The connection between discrete spacetime and the measurement problem in quantum mechanics suggests that the fundamental discreteness of space and time might provide a natural solution to questions about quantum measurement and the emergence of classical reality from quantum phenomena. Perhaps most remarkably, if spacetime is fundamentally digital, this would represent the most profound example of emergent phenomena in nature, the continuous reality of our everyday experience emerging from discrete quantum processes operating at the Planck scale. Understanding this emergence could revolutionize our comprehension of space, time, and reality itself. The digital view of spacetime suggests that the Planck length represents not just a measurement limit, but the actual resolution of reality. Just as digital images are composed of discrete pixels, Physical space might be composed of discrete units of Planck length, making this the fundamental pixel size of the universe. As we'll explore next, this discrete structure of spacetime has profound implications for how information is stored and processed in the universe, potentially revealing deep connections between physics, computation, and the nature of reality itself. Chapter 8: Information and Entropy. The relationship between the Planck length and fundamental limits on information storage reveals that space itself might be nature's ultimate information processing system, with the smallest possible distance directly connected to the smallest possible unit of information. This deep connection between geometry and information suggests that the Planck length represents not just a spatial scale, but the fundamental resolution at which the universe processes information about its own structure. The Bekenstein bound, derived by Dr. Jacob Bekenstein in the 1970s, provides a fundamental limit on how much information can be stored in any finite region of space. This bound states that the maximum entropy, and therefore information content, of any region is proportional to the area of its boundary, measured in Planck units, not its volume as classical intuition might suggest. Mathematically, the Bekenstein bound states that the maximum entropy S of any region is bounded by S is less than or equal to A4LP squared, where A is the area of the boundary and LP is the Planck length. This means that each Planck area can store at most one bit of information, establishing a direct connection between spatial geometry and information capacity. Black hole thermodynamics provides the most dramatic example of this information area relationship. Stephen Hawking showed that black holes have temperatures and entropies, with the entropy being proportional to the area of the event horizon rather than the volume of the black hole. This suggests that black holes store information on their surfaces rather than in their interiors. The black hole information paradox emerges from the tension between quantum mechanics, which requires information to be preserved, and black hole evaporation through Hawking radiation, which appears to destroy information. Understanding how information is preserved during black hole evaporation might require new insights into the relationship between spacetime geometry and information storage. Dr. Leonard Susskind's work on the holographic principle extends the information area relationship to all regions of space, proposing that the information content of any volume is encoded on its boundary. This suggests that our three-dimensional experience might emerge from more fundamental two-dimensional information processing occurring at boundaries. The holographic principle implies that the Planck length provides the fundamental resolution for information encoding on spatial surfaces. Each Planck area of any surface can encode exactly one bit of information, making the Planck length the pixel size for nature's information storage system. Quantum error correction becomes crucial for understanding how information is preserved and processed at the Planck scale. Recent work by John Preskill, Patrick Hayden, and others has revealed deep connections between quantum error correction, black hole physics, and the structure of spacetime itself. The ADS-CFT correspondence, discovered by Juan Maldacena, provides a concrete example of holographic information encoding where quantum gravity in higher dimensional space is equivalent to quantum field theory without gravity on the boundary of that space. This demonstrates that gravitational physics can emerge from information processing at boundaries. Entanglement plays a crucial role in holographic information storage, with the geometric properties of spacetime emerging from the entanglement structure of quantum states living on boundaries. The connectivity of space might reflect a pattern of quantum correlations between different regions of the holographic boundary. The firewall paradox, proposed by Ahmed Almhiri and colleagues, highlights fundamental tensions between quantum mechanics, general relativity, and information theory at black hole horizons. Resolving this paradox might require understanding how information is processed and encoded at the Planck scale. Quantum computational complexity provides new tools for understanding information processing in spacetime. The complexity of quantum states that encode spacetime geometry might be related to the geometric properties of the space itself, with the Planck length setting fundamental limits on computational complexity. The it from bit hypothesis, proposed by John Wheeler, suggests that all physical phenomena emerge from information processing, rather than information emerging from physical phenomena. In this view, the Planck length represents the fundamental scale at which reality computes itself through information processing operations. Thermodynamic considerations reveal deep connections between information, entropy, and spacetime geometry. The second law of thermodynamics requires entropy to increase over time, but in quantum systems, information is conserved, creating apparent tensions that might be resolved through understanding information processing at the Planck scale. The covariant entropy bound, developed by Raphael Bousso, extends the Bekenstein bound to arbitrary spacetime regions by relating entropy to the area of light sheets rather than just spatial boundaries. This bound applies to dynamical spacetime regions and provides constraints on information processing during cosmic evolution. Causal structure plays a crucial role in information processing because information cannot propagate faster than light. The discrete structure of spacetime at the Planck scale might impose fundamental limits on information transmission that complement the speed of light limit from special relativity. Quantum field theory in curved spacetime reveals how information processing depends on spacetime geometry. The Hawking radiation emitted by black holes carries information about the black hole's formation and evolution, but extracting this information might require understanding quantum information processing at the Planck scale. The emergence of classical spacetime from quantum information might explain why space appears three-dimensional and time one-dimensional. The optimal information processing capacities of systems with different numbers of dimensions might select the four-dimensional spacetime we observe. Error correction in spacetime itself might be necessary to maintain the coherence of geometric information over cosmic timescales. Just as quantum computers require error correction to maintain quantum states, spacetime might require natural error correction mechanisms to preserve geometric relationships. The relationship between computation and physics becomes particularly important when considering whether spacetime is fundamentally computational. If information processing at the Planck scale gives rise to spacetime geometry, then physical laws might emerge as computational algorithms operating on quantum information. Digital physics theories propose that the universe is literally a computational process, with the Planck length representing the spatial resolution and the Planck time representing the temporal resolution of the cosmic computation. In these theories, physical evolution becomes equivalent to information processing. The maximum computational capacity of any region of spacetime is limited by the Bekenstein bound, which constrains how much computation can occur within any finite region. This computational bound is achieved when the region is filled with matter at the maximum possible density, effectively becoming a black hole. Landauer's principle connects information processing to thermodynamics by showing that erasing information requires a minimum energy expenditure. At the Planck scale, this principle might impose fundamental constraints on how spacetime can evolve while preserving or erasing geometric information. The no-cloning theorem prevents perfect copying of quantum information, which might explain why spacetime has a unique evolution rather than branching into multiple copies. The fundamental impossibility of cloning quantum information might be built into the structure of spacetime at the Planck scale. Quantum teleportation demonstrates how quantum information can be transmitted through entanglement and classical communication without transmitting the information carriers themselves. Similar mechanisms might operate in spacetime, allowing geometric information to be transmitted through quantum correlations. Perhaps most remarkably, the connection between information and the Planck length suggests that space itself is nature's information storage and processing system. The smallest possible distance might represent the fundamental resolution at which the universe stores and manipulates information about its own geometric structure. The study of information at the Planck scale reveals that geometry and information are more deeply connected than previously imagined. Understanding this connection might be key to developing a complete theory of quantum gravity and could revolutionize our understanding of space, time, and computation. As we'll explore next, these theoretical insights about information and space-time structure might eventually lead to experimental tests that could reveal whether space truly has a discrete structure at the Planck scale. Chapter 9. Experimental challenges testing theories about the Planck length represents one of the most formidable experimental challenges in physics, requiring techniques that can probe scales more than 15 orders of magnitude smaller than anything directly accessible to current technology. The energy scales needed to directly explore Planck length physics exceed those of the most powerful particle accelerators by factors so enormous that entirely new approaches to experimental physics might be necessary. The fundamental problem is one of energy requirements. To probe distances of order the Planck length using conventional techniques requires particles with wavelengths comparable to that distance, which means energies near the Planck energy of approximately 1019 GeV. This is about 1016 times higher than the energies achieved at the Large Hadron Collider, the world's most powerful particle accelerator. Dr. Gerard T. Hoof first analyzed the fundamental limits on measuring distances smaller than the Planck length, showing that the energy required to achieve such resolution would create microscopic black holes that would immediately evaporate through Hawking radiation. This represents an absolute barrier to direct measurement that cannot be overcome through technological improvements. Indirect approaches to Planck scale physics focus on detecting subtle effects that might be amplified or preserved at larger scales. These effects can include modifications to the propagation of light or matter waves, corrections to particle interactions, or signatures in the cosmic microwave background radiation from the early universe when Planck scale physics dominated. Lorentz invariance violation represents one potential signature of discrete spacetime structure. If space has a fundamental lattice structure at the Planck scale, this might break the perfect symmetry of spacetime assumed by special relativity, leading to effects that depend on the direction or energy of particle motion. High-energy astrophysics provides natural laboratories where extreme energies approach those needed for Planck-scale physics. Gamma-ray bursts, active galactic nuclei, and cosmic ray interactions achieve energies many orders of magnitude higher than terrestrial particle accelerators, potentially revealing new physics operating near fundamental scales. The Planck collaboration has used cosmic microwave background observations to search for signatures of discrete spacetime structure from the early universe. The patterns of temperature fluctuations in the CMB might preserve information about quantum, gravitational effects that operated when the universe was much smaller and denser. Dr. Giovanni Amelino Camiglia has proposed tests of quantum gravity phenomenology using high-energy astrophysical observations. These tests look for energy-dependent modifications to the speed of light or other fundamental parameters that might arise if spacetime has a discrete structure at the Planck scale. Precision measurements of fundamental constants provide another avenue for testing Planck-scale physics. If the values of constants, like the fine structure constant or the gravitational constant, depend on the discrete structure of spacetime, precision atomic spectroscopy or gravitational experiments might detect these dependencies. Gravitational wave astronomy offers new opportunities to probe extreme spacetime curvature where quantum gravitational effects might become observable. The merger of black holes or neutron stars creates conditions where spacetime curvature approaches scales where discrete structure might become apparent. The laser interferometer, Gravitational Wave Observatory, LIGO, and similar detectors might eventually achieve sensitivity sufficient to detect quantum gravitational corrections to Einstein's general relativity. These corrections could manifest as modifications to gravitational wave propagation or generation mechanisms. Tabletop experiments testing Newton's inverse law at very short distances provide constraints on modifications to gravity that might arise from discrete spacetime structure. These experiments have probed gravitational interactions down to distances of about 0.1 millimeters, still many orders of magnitude larger than the Planck length. Dr. Eric Adelberger's group at the University of Washington has conducted the most precise short-range gravity experiments, using torsion balances to test whether gravitational attraction follows Newton's law at microscopic scales. While these experiments haven't reached the Planck scale, they constrain theories that predict deviations from standard gravity. Atomic interferometry experiments can achieve extraordinary sensitivity to spacetime curvature and might eventually detect quantum gravitational effects. These experiments use quantum superposition of atomic wave functions to measure accelerations and forces with precision approaching fundamental quantum limits. Quantum sensing techniques using entangled particles or squeezed quantum states might achieve sensitivity sufficient to detect discrete spacetime effects. These approaches exploit quantum correlations to enhance measurement precision beyond what classical techniques can achieve. The study of black hole analogs in condensed matter systems provides opportunities to test aspects of Planck-scale physics in controllable laboratory environments. While these analogs cannot directly probe quantum gravity, they might reveal universal aspects of how discrete structure affects wave propagation and information processing. Dr. William Unruh's work on sonic black holes and flowing fluids demonstrates how some aspects of black hole physics can be studied using acoustic waves in condensed matter systems. These analogs might provide insights into how information is processed at event horizons and how discrete structure affects these processes. Cosmological observations of the early universe provide perhaps the best opportunity to detect signatures of Planck-scale physics because the universe was once small enough that quantum gravitational effects dominated cosmic evolution. The cosmic microwave background, primordial gravitational waves, and large-scale structure formation might preserve information about these early epochs. The European Space Agency's Planck mission achieved unprecedented precision in measuring CMB temperature fluctuations, constraining models of cosmic inflation and early universe physics. Future missions might achieve sufficient sensitivity to detect signatures of discrete spacetime structure from the Planck epoch. Primordial gravitational waves from cosmic inflation might carry information about spacetime structure during the earliest moments after the Big Bang. These waves would have wavelengths stretched from microscopic scales to cosmic scales, potentially preserving information about Planck-scale physics in observable form. Particle physics experiments at the energy frontier continue pushing toward higher energies that might eventually reveal new physics connected to quantum gravity. While direct access to the Planck scale remains impossible, intermediate energy scales might reveal physics that bridges between current understanding and Planck scale phenomena. The proposed International Linear Collider and other next-generation particle accelerators might achieve energy sufficient to probe physics at scales where quantum gravitational effects begin to influence particle interactions. These experiments could detect virtual black hole production or other exotic phenomena. Precision measurements of the electron's magnetic moment, the fine structure constant, and other fundamental parameters have achieved extraordinary accuracy and might eventually detect corrections arising from discrete spacetime structure. These measurements provide stringent tests of quantum field theory and could reveal new physics. Laboratory tests of the equivalence principle using falling test masses provide constraints on modifications to gravity that might arise from quantum gravitational effects. These experiments test whether different types of matter fall at exactly the same rate in gravitational fields, as general relativity predicts. The development of new measurement techniques based on quantum technology might eventually enable direct probes of spacetime structure at unprecedented scales. Quantum computers, quantum sensors, and quantum communication systems exploit quantum correlations in ways that might reveal quantum gravitational effects. Perhaps most importantly, the experimental challenges of probing the Planck scale are driving the development of new, theoretical approaches that make testable predictions without requiring direct access to Planck-length physics. These approaches focus on finding amplified signatures or preserved information from Planck scale processes. The combination of theoretical advances and experimental innovation continues pushing the boundaries of what can be tested about fundamental spacetime structure. While direct measurement of the Planck length remains impossible, the search for its signatures in accessible phenomena continues revealing new insights into the nature of space and time. As we'll explore next, the implications of the Planck length extend far beyond abstract physics to questions about computation, information processing, and the fundamental nature of reality itself. Chapter 10: Computational Implications. The discrete structure of spacetime at the Planck scale has profound implications for computation and information processing, suggesting that the universe itself might be a vast computational system with the Planck length, determining the fundamental resolution at which reality processes information about its own evolution. Understanding these computational aspects reveals deep connections between physics, computer science, and the nature of reality itself. The idea that the universe might be fundamentally computational emerges from the observation that all physical processes involve information processing at some level. Quantum systems store and manipulate information through their quantum states, and the evolution of these states follows computational rules described by quantum mechanics. If spacetime itself is discrete at the Planck scale, then physics becomes literally digital. Digital physics theories, developed by Edward Fredkin, Stephen Wolfram, and others, propose that the universe is equivalent to a vast cellular automaton, a computational system where simple rules operating on discrete cells generate complex behaviors. In these theories, the Planck length and Planck time provide the spatial and temporal resolution of the cosmic computation. The computational capacity of any region of spacetime is fundamentally limited by the Bekenstein bound, which restricts the maximum information content to be proportional to the area of the region's boundary. This implies that the universe cannot perform arbitrary computations, but is constrained by fundamental, physical limits on information processing. Dr. Seth Lloyd at MIT has calculated the maximum computational capacity of the observable universe based on physical limits from thermodynamics, quantum mechanics, and general relativity. His analysis shows that since the Big Bang, the universe could have performed at most about 10,120 operations on about 1,090 bits of information. These computational limits are achieved when matter is arranged in the most computationally efficient possible configuration, essentially becoming a black hole. Black holes represent the ultimate computers in the sense that they store the maximum possible information in their event horizons and process this information through their thermodynamic evolution. Quantum computation at the Planck scale faces fundamental challenges because quantum coherence becomes difficult to maintain when gravitational effects become important. The interaction between quantum information and spacetime geometry might impose limits on quantum computational processes that don't exist in ordinary quantum computers. The holographic principle suggests that computation in three-dimensional space might be equivalent to computation on two-dimensional boundaries, potentially revolutionizing our understanding of computational complexity. If three-dimensional physics emerges from two-dimensional information processing, then the computational complexity of physical processes might be lower than previously thought. Quantum error correction becomes crucial for understanding how information is preserved and processed reliably in discrete spacetime. The universe must have natural error correction mechanisms to maintain the coherence of quantum information over cosmic timescales, just as quantum computers require error correction to maintain quantum states. Dr. John Preskill and others have discovered deep connections between quantum error correction, black hole physics, and spacetime geometry. These connections suggest that spacetime itself might be an emergent phenomenon arising from quantum error correction, operating on more fundamental quantum information. The Church-Turing thesis, which states that any effectively computable function can be computed by a Turing machine, takes on new meaning when applied to physics. If the universe is fundamentally computational, then all physical processes must be computable in principle, constraining the types of physical laws that are possible. Computational complexity theory provides tools for understanding the intrinsic difficulty of simulating physical systems. Some quantum systems appear to require exponential resources to simulate classically, suggesting that quantum computers might be fundamentally more powerful than classical computers for certain types of problems. The halting problem and other undecidable problems in computer science raise questions about whether physical systems can solve problems that are fundamentally unsolvable by any algorithm. If physics is fundamentally computational, then the universe cannot solve undecidable problems, potentially constraining physical evolution. Reversible computation becomes important at the Planck scale because fundamental physical laws are reversible. They work the same way forward and backward in time. Landauer's principle shows that irreversible computation necessarily dissipates energy, so the universe might need to operate as a reversible computer to avoid violating conservation of energy. Dr. Charles Bennett has shown that computation can be made reversible through careful design of computational processes that preserve all input information while generating desired outputs. Such reversible computers dissipate much less energy than conventional, irreversible computers and might represent the natural mode of cosmic computation. The maximum clock speed of computation is limited by fundamental physical constants. No computational process can operate faster than the Planck frequency of about 1043 operations per second because this represents the fundamental time resolution at which spacetime can evolve. Parallel processing in discrete spacetime allows different regions of space to perform computations simultaneously, potentially enabling the universe to achieve enormous computational throughput through massive parallelization. Each Planck scale region could function as an independent processor in a cosmic parallel computer. The relationship between computation and thermodynamics becomes crucial at the Planck scale, where energy densities approach fundamental limits. Any computation requires energy to operate, and the efficiency of this energy usage might constrain the types of computational processes that can occur naturally in spacetime. Quantum field theory in discrete spacetime might be equivalent to quantum computation on a spatial lattice, with quantum fields represented as quantum information distributed across the lattice sites. The evolution of quantum fields would then become equivalent to quantum computational processes operating on this distributed quantum information. Emergent computation describes how complex computational behaviors can arise from simple local rules operating on discrete systems. The complex physics we observe at large scales might emerge from simple computational rules operating at the Planck scale, similar to how complex patterns emerge in cellular automata. The simulation hypothesis, popularized by philosopher Nick Bostrom, proposes that our reality might be a computer simulation. If the universe is fundamentally computational at the Planck scale, this raises questions about whether simulated realities could be distinguishable from real reality. Information theoretic approaches to physics suggest that physical laws might be computational algorithms that the universe uses to process information about its own state. Conservation laws, symmetries, and other fundamental principles might emerge as computational constraints on information processing. Machine learning and artificial intelligence techniques are being applied to discover patterns in physical systems and might eventually reveal computational principles underlying natural phenomena. These approaches could help identify the computational algorithms that the universe uses to evolve from one state to another. The measurement problem in quantum mechanics takes on new meaning if spacetime is fundamentally computational. Quantum measurements might be computational processes where the universe determines definite outcomes from quantum superpositions through algorithmic procedures operating at the Planck scale. Complexity theory provides tools for understanding which physical processes are efficient to compute and which require exponential resources. The computational complexity of simulating different physical systems might reveal fundamental differences between different types of physical phenomena. Perhaps most remarkably, the computational view of spacetime suggests that asking questions about the nature of reality is equivalent to asking questions about the computational processes that the universe uses to process information about itself. Understanding computation at the Planck scale might be key to understanding existence itself. The implications extend to questions about consciousness and intelligence. If the universe is fundamentally computational, then consciousness might emerge from computational processes operating in the discrete spacetime substrate, making intelligence a natural consequence of cosmic information processing. Future developments in quantum computing, artificial intelligence, and computational physics might provide new insights into the computational nature of reality. These fields are developing tools that could eventually test whether the universe operates according to computational principles at the Planck scale. As we approach our final exploration, we'll consider how understanding the Planck length as the smallest possible distance connects to the deepest questions about reality, existence, and our place in a universe that might be far stranger and more computationally sophisticated than we ever imagined. Chapter 11. Philosophical Implications. The discovery that there exists a smallest possible distance fundamentally challenges our basic assumptions about the nature of space, time, and reality itself, raising profound philosophical questions about the continuity of existence, the relationship between mathematics and physics, and whether the universe has a fundamentally digital rather than analog character. These implications extend far beyond technical physics to touch the deepest questions about what it means for anything to exist at all. The existence of a fundamental limit to spatial subdivision suggests that the infinite divisibility that characterizes mathematical continua does not apply to physical space. While we can mathematically divide any length by 2 indefinitely, physical space apparently cannot be divided beyond the Planck length, representing a fundamental departure from the mathematical idealization of continuous geometry. This discreteness challenge as the philosophical tradition dating back to ancient Greek philosophy that assumes space and time form continuous manifolds. Zeno's paradoxes, which demonstrated apparent contradictions in continuous motion, might find resolution in discrete spacetime where motion occurs through discrete jumps rather than continuous transformation. The relationship between mathematics and physical reality becomes particularly puzzling when we consider that mathematical spaces can have any number of dimensions and any degree of continuity, while physical space appears to have exactly 3 dimensions and fundamental discreteness. This suggests that mathematics might be more general than physics, raising questions about why physical reality selects specific mathematical structures. Dr. Eugene Wigner's famous essay on the unreasonable effectiveness of mathematics in the natural sciences identified the puzzle of why mathematical concepts developed for purely abstract reasons often find precise applications in describing physical phenomena. The emergence of the Planck length from pure mathematical combinations of fundamental constants exemplifies this mysterious relationship. The question of reductionism versus emergence takes on new meaning when considering discrete spacetime. If space and time are fundamentally discrete, do all larger-scale phenomena emerge from processes operating at the Planck scale? Or do emergent properties at larger scales have independent reality that cannot be reduced to Planck-scale processes? Determinism and free will acquire new dimensions when spacetime itself becomes quantum mechanical and discrete. If reality operates through quantum computational processes at the Planck scale, then determinism might be replaced by algorithmic evolution that includes fundamental randomness, potentially providing space for genuine free will within natural law. The nature of causality requires re-examination if spacetime has discrete structure. Classical causality assumes continuous causal chains where every effect has an immediately preceding cause. But discrete spacetime might involve discontinuous causal jumps between discrete spacetime events, fundamentally altering causal relationships. Information theory suggests that the universe might be fundamentally informational rather than material, with matter and energy being emergent phenomena arising from more basic information processing. If the Planck length represents the fundamental resolution of cosmic information processing, then reality might be more like computation than classical mechanics. The hard problem of consciousness, explaining how subjective experience arises from physical processes, might find new approaches. If consciousness emerges from information processing at the Planck scale, the discrete structure of spacetime might provide the digital substrate necessary for information processing, sophisticated enough to support consciousness. Dr. David Chalmers and others have explored whether consciousness might be a fundamental feature of reality rather than an emergent property of complex systems. If spacetime itself processes information at the Planck scale, then some form of information processing, and perhaps proto-consciousness, might be built into the basic structure of reality. The relationship between observation and reality becomes even more complex if spacetime itself is quantum mechanical. The measurement problem in quantum mechanics traditionally concerns how classical reality emerges from quantum possibilities. But if spacetime is quantum, then observation might involve quantum processes operating at the most fundamental level. Realism versus anti-realism debates acquire new dimensions when considering whether discrete spacetime structure is real or merely a useful mathematical model. If the Planck length cannot be directly measured due to fundamental physical limitations, what does it mean to claim that it represents the actual structure of space? The principle of sufficient reason, which states that everything must have a reason or explanation, faces challenges when applied to fundamental constants and the Planck length. Why do the fundamental constants have the specific values that produce the observed Planck length rather than some other value? Is this selection purely arbitrary, or does it reflect deeper principles? Modal realism, the philosophical position that all possible worlds are equally real, raises questions about whether universes with different Planck lengths exist in parallel realities. If fundamental constants could have different values, do all possible combinations exist somewhere in a vast multiverse of different physical realities? The anthropic principle provides one approach to understanding why the Planck length has its observed value by arguing that only universes with specific values can support observers capable of measuring these constants. This introduces consciousness into fundamental physics in ways that some philosophers find unsatisfying while others see as inevitable. Temporal philosophy must grapple with the implications of the Planck time as the shortest possible interval. Does this mean that time is fundamentally discrete, or does continuous time emerge from discrete processes? The nature of temporal flow and the experience of duration might require fundamental revision. The relationship between mind and matter becomes particularly mysterious if both emerge from computational processes operating at the Planck scale. Substance dualism, which treats mind and matter as fundamentally different substances, becomes problematic if both are aspects of cosmic information processing. Emergence versus reduction takes on crucial importance when considering how macroscopic physics arises from Planck scale processes. Strong emergence, where higher-level phenomena have genuine causal power irreducible to lower levels, might be necessary if Planck scale processes cannot fully determine large-scale behavior. The nature of laws versus initial conditions requires re-examination if spacetime is fundamentally discrete. Traditional physics distinguishes between laws that govern evolution and initial conditions that specify starting states. But discrete spacetime might make this distinction meaningless if the structure of space and time is itself part of the initial conditions. Teleological questions about purpose and direction in cosmic evolution acquire new meaning if the universe operates as an information processing system. The apparent fine-tuning of fundamental constants and the emergence of complexity might reflect computational optimization rather than purposeless mechanical evolution. The relationship between possibility and actuality becomes complex if reality is fundamentally computational. Mathematical possibilities that cannot be computed might be physically impossible, while physically possible events might be constrained by computational complexity considerations rather than just energy and momentum conservation. Identity and persistence through time raise new questions if spacetime is discrete. Personal identity might involve continuity of information processing rather than continuity of material substance. And the discreteness of time might make temporal persistence more like a sequence of discrete existences than continuous being. The nature of scientific knowledge itself requires re-examination if fundamental limits exist on measurement and observation. The Planck length might represent not just a practical limit, but a fundamental, epistemological boundary beyond which certain types of knowledge are impossible in principle. Metaphysical questions about the nature of existence take on new urgency if reality is fundamentally informational and discrete. Does existence require information processing, or can things exist without being processed? Is reality more like a cosmic computer program than a mechanical clockwork? The problem of other minds becomes particularly acute if consciousness emerges from Planck-scale information processing. How can we determine whether other systems process information in ways that give rise to conscious experience? Is consciousness a binary property, or does it admit of degrees corresponding to computational complexity? Perhaps most profoundly, the existence of a smallest possible distance suggests that infinity might not be physically realizable, even though it remains mathematically meaningful. This finite, discrete character of space might indicate that reality is fundamentally different from mathematical abstractions in ways that require new philosophical frameworks. The implications of discrete spacetime extend to questions about death, meaning, and the significance of human existence in a universe that might be more like a cosmic computation than a mechanical system. Understanding our place in such a reality might require entirely new philosophical approaches that bridge physics, computation, and human experience. As we conclude our exploration of the Planck length, we must consider how this fundamental limit on distance measurement reveals the universe to be far stranger and more wonderful than classical physics ever suggested, raising questions that will likely occupy philosophers and physicists for generations to come. Throughout this journey to the deepest scales of reality, we've discovered that the Planck length represents far more than just a very small distance. It marks the fundamental boundary where space and time themselves transform from the familiar, continuous stage of classical physics into something far stranger and more quantum mechanical. This tiny distance of 1.616 times 10 to 35 meters embodies one of the most profound insights in modern physics, that reality itself has a fundamental granular structure. We began by placing the Planck length in the vast hierarchy of scales that span our universe, recognizing that this distance is smaller relative to an atom than an atom is relative to you. Yet despite its inconceivable tininess, the Planck length emerges naturally from the fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant, suggesting that this scale is built into the basic architecture of physical law. The quantum limits we explored reveal why the Planck length isn't just difficult to measure. It represents an absolute barrier imposed by the laws of physics themselves. Heisenberg's uncertainty principle, combined with the enormous energies required to probe such small distances, creates fundamental obstacles that cannot be overcome by any conceivable improvement in experimental technique. When gravitational effects enter the picture at the Planck scale, they create additional barriers that reinforce the quantum limits. The energy needed to probe Planck-length distances would create microscopic black holes that immediately evaporate through Hawking radiation, making meaningful measurement impossible even in principle. Gravity, usually the weakest force, becomes as important as quantum effects at this scale. The concept of spacetime foam revealed how quantum mechanics and gravity combine to create a picture of space and time as fundamentally turbulent and uncertain at the Planck scale. The smooth spacetime of Einstein's relativity emerges only as an average over violent quantum fluctuations that make the familiar concepts of distance and duration meaningless at the smallest scales. We discovered how the fundamental constants of nature combine in a unique way to define the Planck length, suggesting that this distance represents a natural unit built into reality rather than an arbitrary human convention. The appearance of the speed of light gravitational constant and Planck's constant in this definition reveals deep connections between quantum mechanics, relativity, and gravity. The quest for quantum gravity showed how attempts to unify general relativity with quantum mechanics naturally lead to the Planck scale as the regime where new physics must emerge. String theory, loop quantum gravity, and other approaches all suggest that spacetime has fundamentally different properties at the Planck scale than it does in our everyday experience. The possibility that space and time are fundamentally digital rather than analog represents one of the most radical implications of Planck scale physics. Just as matter appears continuous but actually consists of discrete atoms, space and time might appear smooth but actually be made of indivisible quantum units with the Planck length, setting the fundamental resolution. Information and entropy connections revealed that the Planck length might represent the fundamental pixel size of nature's information processing system. The holographic principle suggests that each Planck area can store exactly one bit of information, making space itself into a vast information storage and processing system operating at the quantum level. The experimental challenges we discussed show why testing Planck-scale physics pushes the boundaries of what's possible, requiring entirely new approaches that look for amplified signatures or preserved information from quantum gravitational processes. While direct measurement remains impossible, indirect tests continue probing the fundamental structure of spacetime. Computational implications suggest that if space and time are discrete at the Planck scale, then the universe itself might be equivalent to a vast quantum computer processing information about its own evolution. This computational view of reality connects physics to computer science in ways that could revolutionize both fields. The philosophical implications challenge our basic assumptions about the nature of existence, suggesting that reality might be fundamentally informational and discrete rather than continuous and mechanical. These insights raise profound questions about consciousness, free will, and the relationship between mathematics and physical reality. As you go about your day after learning this, remember that every step you take covers distances containing approximately 1035 Planck lengths. Every second that passes contains about y d Planck times. The apparently smooth space and time of your experience emerges from quantum processes operating at scales so small they challenge human comprehension. When you look at the smooth surface of a table, consider that at the Planck scale, it's probably a chaotic foam of quantum fluctuations, where the very concepts of surface and smoothness break down. The solid matter around you emerges from discrete quantum, process is operating in a fundamentally granular spacetime substrate. The Planck length connects the largest scales of cosmology to the smallest scales of quantum mechanics, revealing that understanding the nature of space and time requires grappling with the most fundamental questions about reality itself. This tiny distance embodies the unity of physics and demonstrates that the universe operates according to principles far stranger than everyday experience suggests. Perhaps most remarkably, the Planck length represents humanity's encounter with the absolute limits of spatial measurement and possibly with the fundamental structure of existence itself. It reveals that there are aspects of reality so basic and fundamental that they transcend the realm of direct observation and enter the realm of pure theoretical understanding. The study of the Planck length also shows how physics sometimes leads to conclusions that seem to violate common sense while being rigorously supported by mathematical analysis and experimental constraints. The idea that space has a smallest possible distance seems counterintuitive, yet it emerges inevitably from our best theories of quantum mechanics and gravity. Understanding why the Planck length represents the smallest possible distance has revealed connections between quantum mechanics, gravity, information theory, and computation that weren't apparent when these fields developed independently. This unity suggests that reality operates according to deep principles that transcend traditional disciplinary boundaries. If you made it this far, subscribe and give a thumbs up. Check out my video on why time might be quantized. I'm sure you'll love exploring how the fundamental nature of time connects to the discrete structure of space we've been discussing. The Planck length stands as the ultimate boundary in our exploration of space, marking the point where distance itself is born from quantum foam and where the familiar concept of measuring smaller and smaller things gives way to the recognition that smallness itself has an absolute limit, a limit that reveals space and time to be far more mysterious and wonderful than our everyday experience could ever suggest.